Hello, I'm Santiago Vargas. As you'll probably notice, I'm not in the room right now. I'm currently finishing up my quarter in LA. I will hopefully be in Chile in a couple of weeks, but I still wanted to give everyone a briefing on what research I'm going to be conducting as part of my Fulbright. And my project is going to be the application of computational chemistry to the study of energetic processes, and I'll give a few examples, and quantum computing. So before we get into science, I just want to talk a little bit about my background, my academic lineage. So I just graduated in May from Harvard with my degree in chemistry and physics, and in the fall I started my PhD in computational chemistry in LA, as I mentioned. And my two advisors that have really shaped the scientist I am are Dr. Alan Aspurguzik, and with him I was working on a superconducting circuit project. We were trying to optimize these circuits to create hopefully qubits for quantum computing, and that was through a lot of AI, a lot of machine learning, and just high throughput computing in general. So I was exposed to a lot of CS through this physics project. In addition to that, right now my mentor PI is Anastasia Alexandrova, and she's at UCLA, and with her I haven't left the domain of quantum computing, but now we're trying to use molecular systems to probe qubit design to try and build a quantum computer, but from a different perspective. So, as I mentioned, I am a theoretical chemist. Computational chemists kind of go contrary to the standard image of a chemist. So here's the standard image of a chemist. You know, he's working in the hood, mixing fluids. It's, something might explode on his face, a cloud of smoke. He's wearing his safety goggles though, so everything's all right. But chemistry really looks a little bit more like this today. Where you have a computational chemist working with this experimentalist, because as an experimentalist, probably the most common result of research is that you're going to use 6 months to synthesize a chemical. You're going to put it, say, on a solar panel, test its properties, and it's going to be useless. It's not going to help. It's not going to be cutting edge, or it's just not usable. And as computational chemists, we look to inform, experimentalists and people actually creating these substances as to whether it's going to be useful, what properties it's going to have before they even synthesize it. And we'll do that, and my workload really looks like I'm going to submit a job, a calculation, to a server, and AWS is Amazon's cloud computing service, if anyone's not familiar. And I'm going to give a computer a rule set and a set of instructions, and it's going to return to me a calculation that I can interpret and tell an experimentalist this is a good experiment or this is probably not going to work, and save them 6 months, a year or two of work in worst case scenario. And I don't think computational chemistry is necessarily talked about a lot in quotidian, but looking forward to the field, I think an exciting vision is a robotic vision, that we could turn chemistry into sort of an automobile factory where robots are receiving commands and performing experiment, and I just get results. This robotic vision is, why I draw this red arrow for the experimentalists. Hopefully we can cut him out and put him out of a job, or teach him CS so that he can do the same. He or she can do the same. And that's a vision of this field going forward. And why, I guess tangibly, we talked a little bit about the scale and experiments not working, but why is computational chemistry useful and in many cases superior to experimental chemistry, even though they're here in synergy? Is one, the scale of experiments I can do is vastly greater than an experimentalist. I can submit 100 calculations and probe 100 different chemical systems in one morning. Experimentalists could not hope to do that in years, decades, with things not working, faulty experiments, faulty equipment. They could not hope to do that scale of experiment in decades, even their entire career. In addition, if we think about this from an ecological perspective with waste and energy consumption, computation on a per scientist basis is way more eco-friendly than setting up a lab, creating reagents, importing them in, shipping everything. So computational chemistry is also very eco-friendly, especially if you can cut out some of the work that the experimentalist has to do. I also can work with substances like uranium and not receive specific training and still put my life at risk. I can simulate uranium right now on my laptop, and I'm totally fine, totally safe. Another thing is that I think, and this is experimental sciences in general, but I think chemistry in particular, is that you'll perform an experiment, it'll succeed once, and you can't repeat it, or some collaborator, someone who wants to repeat your experiment, can't repeat it. And this could be equipment, this could literally come down to moisture in the air, or where you performed your synthesis. But with a computer, to some degree of certainty at least, you can repeat calculations from one computer to another, and you're going to get the same exact result. And for me, the other reasons I kind of gravitate towards this field is convenience. I can be, assuming I have Wi-Fi on top of Mount Everest, and I can still do science, still do work, or alternatively, I can be in the Chilean Patagonia doing work, and performing scientific calculations. Also, I can in the morning work on a simulation of a medical, protein or medicine, and then at night start probing batteries for their energetic properties. So there's a lot of diversity in like what I can be working on a day-to-day, month-by-month, week-by-week basis. Okay, so we have some sort of motivation, and we want to get our hands dirty in computational chemistry. So for better or worse, computational chemistry starts and ends with the Schrodinger equation. This ends up being a very tricky thing to solve, but let's go into the math a little bit. This psi operator, we call it the psi variable, is a variable that encapsulates both nuclear properties and electronic properties, and encapsulates states, really. And through this variable, we can start talking about how this is the time-dependent Schrodinger equation, how these variables will propagate over time using this equation. And then this other term, that's the other one, is the Hamiltonian. And what it does is it describes energetics within the state. And what that means is this is a fancy math substitution for potential energy and kinetic energy, if in more layman's terms. And using that, you can propagate states over time. And cool, we can do math, we can do CS. But what properties can we derive out from that? And one of the most important ones for me is photoactivity. From solving this equation and trying to find energetics, we can describe the photoactivity of chemical systems. In addition, right, I just mentioned energetics, we can describe whether something is going to be rocket fuel, or is it going to be Teflon? Is it going to be something very inert that doesn't react with other things around it? We can also try to describe how it's going to behave in a solution in a human body, for example, surrounded by proteins, how it's going to interact with things around it in a biological sense. And once we get energetics, we can also start talking about kinetics, so how these molecules are going to react with each other, how quickly they're going to do so, and this is really important for industrial processes, for manufacture of chemicals, medicine, and other processes as well. And then ultimately, all of these things are just a way of alluding that we can calculate electronic and nuclear structure. We can calculate the structure of chemical systems using this equation. So okay, we know how to work with computational chemistry, and now we just briefly should talk about some of the limitations. Computational chemistry isn't an end-all for science. It has its limitations, and for me in particular, my limitations are right here in these two boxes, molecular dynamics and quantum mechanics. So with these two theories, we can describe things, and you'll see it in terms of angstroms, nanometers, and for time scales on the pico and nanosecond scale. And this might seem like a short time scale to humans, and it's definitely not perceivable by humans, but you can already start probing energy processes, electron transfer processes, protein folding events, just using these two domains that seem very limited. And it doesn't scale out to infinity, as I mentioned, and this graph on the right shows that, is that for, all you need to know from this graph is that for higher degrees of accuracy, so this line being more accurate than the one below it, and this one more accurate than the one below that, you are trading off computational time for more accuracy as you scale in molecular size. So something that is 100 atoms large is already not something within the regime of current computation. for anything but density functional theory. Is one of the theories that we use a lot in computational chemistry. So this is a let's say intermediate accuracy theory. So anything more high accuracy is not achievable beyond a couple dozen atoms in the best case scenario. So computational chemistry is limited in its reach. So next slide. Okay, let's skip around. Sorry about that. So we talked about the limitations, and kind of now I just wanted to talk about why Chile and why in particular I'm here or not here, I guess. Is I wanted to work with this professor, Alejandro Torrolave. He's very big in the field of theoretical reaction pathway analysis. So he brings math and physics into trying to describe how chemical reactions proceed. And a lot of the systems he ends up looking at using these theories are energy systems, computing, and catalysis in particular. He has some applications in medicine, but my project doesn't necessarily apply to that. And also, he has a big emphasis, as I mentioned, in energy. And Chile, in more general, has the SERC, the Solar Energy Research Center, where there's a big push towards developing renewable energy, solar energy, for Latin America, really, for the Southern Cone. One particular, and what I mean energy, renewable energy, for the Southern Cone is renewable energy looks very different in Latin America than it might in Germany or the US. In particular, for me, that's important because, say, the solar spectrum in Chile is vastly different just due to the atmosphere in Chile versus Latin America, versus, the US or Europe. And that's important in terms of what science, what theories, what ultimately reagents you're using to create solar energy, for example. So one of my projects to start out with is this quantum computing project, and this is in collaboration with my lab at UCLA, is that we're trying to create these molecular systems that can be used for qubits. So here we have this, it's called an optical cycling center. So you have a larger atom that you can see some of these, terbium, silicon, calcium, carbon atoms that are being used as these optical cycling centers, and the hope is that you can start chaining these centers together to create what in computation is typically called gates. And these gates are actually the most basic structure of logic in computers, the most basic structure of computation in computers, and you use these gates to build up an actual computer. So the hope is that, okay, we'll simulate one optical cycling center, start chaining them together, and then put them on surfaces where we can interconnect many of them to create gates and actual quantum computers. So that's one of the projects. In addition, sorry about that, my computer is lagging. Skip a few slides. Another project is using Alejandro's reaction pathway analysis to look at, this is a CO2 sequestration process, and the hope is that reaction pathway analysis kind of works on, you have the starting product and you have this final product, and you can calculate their spatial dimension of all the atoms here, and the hope is that you can perturb this slowly to this finalized product and get an energy profile along each step. And you can use that to define the reaction speed, how much product you're going to get, how much of reagents you should use, and whether a catalyst in this case could speed up your chemical reaction. So the other thing I hope to bring to the table here is a lot of what I've been doing in the last year or two has been leveraging machine learning to various different projects. One of them was an image processing task. Another one was working with natural language processing. And I've kind of worked in sort of disparate fields with machine learning. I hope to bring that here, is that Alejandro has developed a few theoretical descriptors for how chemical reactions proceed. And I think that one potential interesting outlook that we could take is using machine learning to generate a more generalized theory for how chemical reactions proceed. So a lot of what he's developed will work for certain systems, say electron transfer processes, say protein folding, geometry relaxation events. But the hope is that maybe we could generalize it using something like neural networks, deep convolutional learning, to create a more readily transferable reaction pathway model. And a lot of the work other people in my previous lab had done in the Guzik lab is trying to develop machine learning for chemical representation. So basically how you teach a computer to interpret chemistry. So in this case, how do you teach a computer to read a benzene ring, for example? But that's outside of what I'm doing here. I just hope to take a little bit of inspiration from that field. All right, with that, I conclude the talk about my research. And you might just say, all right, cool. But as Mason mentioned, this sort of session is also to hopefully foster some sort of collaboration. And I think, sure, maybe not everyone's working computational chemistry or even energy necessarily, but I think one thing that more and more is going to be true in the future is that anyone working in any quantitative science is going to start looking towards machine learning and data science, sort of in the way that now you might look at a linear regression or basic Excel functionality. I think machine learning is going to enter into more common use in social sciences, in biology, and in kind of everything that has numbers and data appended to it. And that being said, I think one area for collaboration that I'd be pretty interested in, just because it would, make me out of my comfort zone, is using you guys as domain experts and potentially me helping out with the machine learning or data science component of it. If anyone has any need or interest in pushing towards machine learning, AI, or high performance computing, big simulations of whatever they're doing, I'd be interested in helping out if I could. But at least starting a more interesting conversation, a long conversation, that would be cool. But if not, you can forward any questions to me via email or talk to Mason. He could potentially forward questions. It's when this is showing, it's probably going to be 5 a.m. in LA, so I will probably not be awake. But I will respond to questions as soon as I can. But yeah, hopefully see you guys in a few weeks in Chile.